Hi, everybody. This is just a write-up or a video explanation of the last problem in 8.6. And just so you know, it's definitely one of those end of reading problems where it goes beyond the real scope of expectations. What you're going to do in this class: 1, 2, 3, 4, 5, 6, 7. So one thing I wanted to start with was just a realistic drawing of what we're working with. 1, 2, 3, 4. So I've constructed these circles where it really says a circle of radius 4 is rotating outside a circle of radius 7. Write a parametric equation to describe the position of a point on the outside of that circle. So there's really a lot of parameters that aren't defined, no pun intended, about this problem. Like where is the point starting at, or how do we define how much time does it take for this to happen? So this is going to kind of make some base assumptions, and you could write a different equation based on different base assumptions. So first of all, I'm going to put a point right there and just say, that's the point we're talking about. That one right there. This point rotating around this circle. So really, we're going to look at two components. This is difficult because you're going to write an equation in relation to x, an equation in relation to y, but those both have multiple components involved. And again, this one's a choice, but one very simple motion that's happening here is this center point of this smaller wheel is just rotating in a circle outside of this. It's not going to fluctuate. It's not going to matter how that outer wheel is rotating. It's just that center point is always going to be 11 away from the center of the larger wheel. So the first thing we're going to do is just kind of almost as an anchor, put that center point down and describe that. So this whole thing is going to just start with 11 times the cosine of t. And t we're just going to define as time, as in as time's ticking along, this ball is rolling around the circle. But it gets a little more complicated, because if that was the whole problem, we could just say that. We could just say, oh, it takes 2 pi to go around, anyway, for this thing to rotate, and it's just that's it. But because it has this extra thing where what's happening with the x variable is it starts here, kind of at 7 away from the center of this, or you could think of that as 7 units to the right of the center. But then as it rolls, it's going to roll as much as 15 away from the center. And I say that because we've got this 7, this 4, and another radius of 4. The furthest this will ever be will be 15 away. And then it'll be at 11, and then it'll kind of be, this point will always be between 7 and 15 units away from the center of this larger circle. So notice that if we think of this as starting right here, it's actually only 7 away. So if we're at 11 cosine t, that's referring to this point, we actually want to take away 4, and that'll work out if we take away times 4 times the cosine. When this is 1 and it's resting, when this is 1 in its resting place, then that will actually be a subtraction of 4, and that'll bring us back to this point of 7. When it's the furthest away, that'll actually be an addition of 4. So we'll be at 11 plus 4, which will get us to that 15 units away. The only others that we would be done, but we can't just write t here. And the reason we can't just write t here is because this is about the rotation of the smaller circle. And if you think about this smaller circle rotating, and by the way, it would have to rotate counterclockwise in order to move forward, kind of get this action going, then it will roll multiple times by the time it's done one full rotation. So if we define, and notice that in this 11 cosine t, what we really did is we defined this as having a period of 2 pi. Remember that the letter b that's in the equation is always 2 pi divided by b. So this would be 2 pi divided by 1. So the period would be 2 pi. The period of this, well, we don't really know, because we know that this needs to go around multiple times by the time this outer circle with a radius 11 has gone around once. So we need to understand that in this equation, B equals 1. And we don't really know what B is, but if we figure out the period, we can figure out B. So the period of this larger is by the time, the way to think of this is by the time this rotates, and I'm going to call it a full circumference of 2 times the radius of 11 times pi. By the time that rotates 22 pi, by the time, in other words, this point right here has gone all the way around, that's traveled a distance of 22 pi. Well, the circumference of, that has a circumference. The circumference of the smaller circle is 2 times radius times pi. So that's going to be 2 times 4 times pi. That's 8 pi. So in order to figure out how many times this has gone around, the question is, how many times will 8 pi go into 22 pi? So if we do 22 pi divided by 8 pi, that is going to be equivalent to the pi's go away, forget about the pi. Really, that's just 22 divided by 8. I'm just going to call that 2.75. 22 divided by 8 is 2 3/4, 11 fourths. But I'm just going to call it 2.75 because for me, it's nice to think of when by the time this has gone around once, this thing has gone around 2.75 times. So another way to think about that is if we think about this period as 6.28 seconds, let's just call it seconds. By the time, if we call 6.28 seconds the amount of time it takes for the larger circle to rotate, this is actually rotated 2.75 times, so that 6.28 divided by 2.75. Remember, a shorter answer would make sense because if it's going around multiple times, 2.75, it has to be rotating faster. So 2.8 divided by 2.75. This is, we don't actually need to use this number. I'm just giving you something to think about. That's about 2.28 seconds. So just to put this in your mind, that if the period of this is in, it takes 6.28 seconds for the larger circle to rotate, that means this thing needs to have gone around multiple times by at that point. So it would be about 2.28 seconds for that period. But I'm going to, instead of calling that 2.28 seconds, I'm just going to call it more accurately 2 pi divided by 2.75. So remember that to calculate B, it's always 2 pi divided by the period. So that would be 2 pi divided by 2 pi divided by 2.75. If I multiply top and bottom by 2.75, that gives us 2 pi times 2.75 divided by 2 pi, which is just going to give us 2.75. So that might have been a lot of talking. Just get back to the number that we talked about earlier. But this number right here is going to be 2.75 pi. All right, so we have done most of the figuring out. I'm about to erase this, so just pause if you need any of this information. I'm going to erase it right now, so pause it right now. That's what you need. I'm going to get rid of this so we can save space. So after all that, all we've really done is describe the X position. Everything we just did just described the X position. The Y position, luckily, is very similar, as in the same period affecting both circles is going to be the same setup. The only thing we need to know is that, so if we look at this initial point and we think about the rotation, so notice that it's rotating this way, so it's on its way down at the start. So the larger circle is similarly going to be, this is really all related to X, this top one. When we talk about Y of t, that's going to be 11 times the sine of t, which again, just referring to this midpoint, the center of the outer circle going around, that is the y coordinate starts at 0 and it's on its way up. That's just like the basic sine function, starting at the midpoint and on its way up. So 11 sine t would work for that. But then you just notice that it's actually losing height because of the rotation of the ball, of the wheel going down at that point. So that's going to be taking away 4 times the sine of that 2.75 other circle. So these are going to be your two equations that make the larger equation go. Hopefully that was helpful to you. I got more videos to record.